let me start with a short introduction. First of all, Alex's talk was about detecting gravitational waves. My talk will be about, how do we go from being confident there is something in the data to being able to say what it is that we found, okay? Now, Alex already mentioned what kind of sources exist out there, but I have better videos, so I'll show it again. Mainly, we have in mind, when we think of gravitational wave sources, four different categories. We have, well, first of all, we typically divide them in transients, which are in our LIGO band and Virgo band for a fraction of seconds to a few seconds, say, and persistent, which can be there forever. Now, in the transient side, we have compact binaries, like the one that Alex focused on, and I also will focus on. So these are any pair of black holes or neutron stars merging together. And then we have basically anything violent that happens in the universe, which has a non-constant quadrupole moment, like a supernovae, will a priori emit gravitational waves. And then on the persistent side, we have spinning neutron stars. As long as they're not perfectly symmetric, they should emit a kind of nearly monochromatic gravitational waves. And then we have the stochastic background, which I shown here, like the surface of a lake during a rainy day. The stochastic background, it's really two things. It can be the sum of all the sources which individually are too weak to be resolved, but all together give you a signal that you can look for, or the stochastic background from the Big Bang, which is too weak for us to go after. All right, so today I'm going to focus on compact binaries and how we see and we say what's in the data. Right, so the first important thing that Alex already hinted at is that the methods that we use to detect these signals are quite different from the methods that we use to measure their parameters and characterize them. And the main reason is that when we search for the signals, we really only want to be sure that there is something in the data which is of astrophysical origin. And we don't really care that much about, how massive it is and, how spinning it is, and so on and so forth. And so you can do that using the template bank method that Alex described. Now, my work starts at this point. My work is from, starting from, there is something which is clearly the same in the two LIGO detector, in Virgo, when Virgo is online. What is it? So how do we do that part? How do we produce this kind of plots? These are some of the plots that have been published by the LIGO and Virgo collaboration. And since one of you asked about masses, these are 2D posteriors for the two-component masses. This is for the binary neutron star. Don't mind the color, that's different priors. But you can see that, in this case, it's 1 point something solar masses. And these are for the binary black holes. Some of the binary black holes we have detected, so these are tens of solar masses. That's M1 and M2. And since the mass ratio was mentioned before, you can clearly see what Alex was saying is that we measure very well this direction, and we don't measure very well that direction. So the small semi-axis is the chirp mass, which we can measure incredibly well. The other semi-axis is the mass ratio. Anyhow, so how do we get these posteriors? The search will not give you this. The search will give you a point estimate of, we found something around, say, 30 solar masses. Right, so before I go through more of the details, I think something that I like to show often when I talk about gravitational wave parameter estimation is that when you look at the gravitational wave in the time domain, like this one, that's the first detection, if you know what you look at, there are actually signatures in the morphology of the waveform itself that can give you hints of what it is that you're looking at. Pretty much the same way in which if you do cosmology and you look at the spectrum of the cosmic microwave background, every feature, every peak, the ratio of the peaks, tells you something about the universe. The same is true for gravitational waves. For example, very trivially, this signal is very short, it's less than a second, and that tells me immediately that it's a very massive object, or actually two objects. And indeed, this was 60 times the mass of the sun. Right, so how many parameters enter into this waveform? If you neglect matter effect, so I will go back to your question in a second, so if you only focus, say, on black holes, which can be treated as point particle, then you have a priori 15 parameters if you deal with circular orbits. You have the two masses, 6 degrees of freedom for the spins, because they are vectors, and there are 2 of them, 2 degrees of freedom for sky position, 2 for the orientation of the orbit with respect to you, the coalescence phase and time, and the distance. If you add matter effect, which you don't care about for detection, but you care if you want to know what these objects are, that gives you 2 extra parameters, 1 for each object, is the tidal deformability. If you want to add eccentricity, that makes it even more complicated. Okay, so it can become arbitrarily more complicated. But at 0th order, you can typically do 15 or 17. Now, the nice thing, which Alex mentioned and also Sasha will talk about, is that we know pretty well how to calculate waveforms in general relativity, which means that if I know the value of the masses, the sky position, and so on and so forth, which I typically call it, as a vector, theta, I can then put these values inside a black box, which is a waveform generator, and that spits out a waveform for me, a time domain or frequency domain waveform. So we know how to do that. Of course, the problem is that we don't know in general what the true masses and other parameters are. Actually, that is exactly what we want to do in this second step. We want to measure those unknown parameters. That is the most generic case in which we don't have any information from, say, an electromagnetic counterpart. There may be optimal situation in which something is found first, say, or even later, because you can fold it a posteriori, and then you can use that. But this is the most generic case in which we're only doing gravitational wave analysis, we don't know anything else. Right, so we have this vector of parameters theta, and we want to measure it. So for those of you who like statistics, there will be some statistics in this talk. We want to measure a posterior distribution of the parameters theta, given the data that we have got in LIGO and Virgo. Now, we typically work within the LIGO-Virgo collaboration in a Bayesian framework, and that means that you can write this posterior, which is what we are after, as the product of 2 terms. The first one, it's called likelihood. The second one is called the prior. Now, what the likelihood, and I will try to give you at least an understanding of what they physically represent. So the likelihood, it's a function that tells you how likely it is to obtain the data that we obtained if the true value of the parameters were theta. That's why theta is on the right side of this vertical bar. The prior, instead, it's what we think we know about theta before looking at the data. Okay, I'll give examples in a second. So the priors are typically very easy to calculate. They're typically analytic. Since in this talk I will have something about computational cost, priors are not the driving cost at all. These are simple functions. For example, the prior we use on the distance of the object, it's something that goes like this square. Why? This comes from the fact that sources should be distributed isotropically and uniform in volume. Okay? So uniform in volume means that there is more space out there, so the probability that a source comes from far away is higher, even before you look at the data. And since they are isotropic, the sky position prior is isotropic. It's just the probability that the tip of an arrow is uniform in a sphere. And for other parameters, like the time at which it arrives or the masses, they are typically uniform. So they're uninformative. Okay, so that's cheap. You can do this with a computer, of course, very, very quickly. What about the likelihood? So first of all, what is the likelihood? How do we calculate the likelihood? So a reminder, the likelihood tells us how likely it is to get the data that we got, given that the true value of the parameters is theta. So it must have this property. The likelihood must be very large if the value of theta I'm putting in my waveform is such that the resulting waveform, the template, looks a lot like what's in the data. So if I'm getting theta right, my likelihood should be higher. Okay? Otherwise, it should be small. Okay, that's the intuition of what the likelihood is and how it should behave. How we calculate it, well, it's another topic. First of all, we need to make some assumption about the noise, and Alex mentioned some of those. So first of all, we assume typically that the data we get out of the detector, it's additive data. So it's the sum of 2 things, Gaussian noise, and hopefully, when there is a gravitational wave that, of course, depends on the true value of the parameters that we don't know in general. Right. And if you do the math, you come up with this very reasonable formula for the likelihood. It's just a Gaussian. It's basically an exponential of minus a scalar product of the data minus the template that you are trying, okay? Why does this work? It works because when theta is roughly equal to the true value that is coming from, somewhere in the sky, then the waveform model you're using will be very close to this signal, so it will cancel it, and you're only left with noise, so you minimize this scalar product. Otherwise, there is a residual, so that's e to the minus something large, so it's something very small. So at least you can see how intuitively this works. All right, and in reality, of course, since we are doing this inside the computer, this guy here is a scalar product, which is an integral, which is a sum in a computer. Right, so it's mostly sums and, calculating these functions. I should also say, although I will not talk about it in detail, that this scalar product is weighted by the noise of the instrument, which kind of makes sense. The fact that this difference is small or large, it's more or less important depending on whether you're doing the measurement in a frequency at which LIGO and Virgo are very good, or in a frequency where LIGO and Virgo don't have a lot of sensitivity. All right, so what do we need to do to calculate posteriors? We want to generate samples, okay? Draw samples from this distribution. A priori, you can think of two possible methods: a brute force approach and stochastic samplings like Markov chain Monte Carlo, or nested sampling, or whatever else you may want to use. Those are the two that we use in LIGO these days more frequently. Let me convince you very quickly why the brute force approach is a very bad idea in this case. So you may think, okay, we want to calculate this posterior. We know how to calculate numerically as a function of prior and likelihood. So I could just calculate these functions everywhere in the parameter space, and then I make a nice plot, or a bunch of nice plots. Now, the reason why that's actually preposterous is because, as I told you, theta is, say, 15 parameters. So you are dealing with a 15D parameter space. Even if each parameter could take only 4 values, then you have 4 to 15 evaluation you need to do, and that's billions already. And of course, in reality, it is not that simple. Each component of theta can take a continuous, set of values. So, we cannot do that. So we do instead stochastic sampling. For example, Markov chain Monte Carlo. Of course, given the time constraints, I will not tell you how this works in detail. But the Markov chain Monte Carlo, it's basically an algorithm that allow you to draw samples from a distribution that you can calculate everywhere, which is our case, because we know how to calculate this. We just calculate the likelihood, we calculate the prior, and we have the posterior. Okay? And the way this works is basically that you have a random chain that goes around in the parameter space, jumping back and forth in a semi-random way. In reality, it's not totally random. You can fold in non-symmetries of your problem. But let's say that it's random, at 0th order of magnitude. And the end product of this sampling is that it gives you a nice posterior distribution. And I will have here a plot. Let me first, before I start it, tell you what you're going to see. Oh, okay, sorry, I started it. Right, so in here you will have two plots that will evolve as a function of time. The first one is just the position of your CNC chain for a parameter in particular. This is the chirp mass, the parameter that Alex mentioned that we measure extremely well. That's the value we put in the data. That's a simulation. We put 6.084. That's the true value. So there are different sets of points here that you see with different colors. These are different CNC chain, which starts in different random part of the parameter space. And if you're doing things correctly, eventually they should all converge to the right spot. The reason why we start several independently is that there is always a non-zero probability that a chain gets stuck in a local minima of the likelihood. Okay, and in here you see the likelihood, actually the log of the likelihood. It doesn't really matter. And now, as the chain progresses, you will see in here the posterior distribution for this parameter, and you will see how it evolves as the chains go farther and farther in the evolution. So for the moment, there is nothing, and now you see the posterior. That's the median in red, and you can see how the chains evolve, and the median should get closer and closer to the true value, and the posterior will look nicer and nicer. You also see that some of the chain at the beginning were far away. That's what we call the burn-in period. And eventually, when they find the right spot, they just wander around. So that's at the 0th order with a many apologize for those of you who actually know how this works in detail, because I know I butchered it, but I only have 25 minutes. How MCNC works. Something worth noticing here is that it's the order of magnitude. The x-axis here is the number of evaluation of the posterior, and hence the likelihood that we have to do. And you can see that it's on the order of millions, up to tens of millions. Compare that with the billions of the brute force approach. Okay, so you can already see why this is the strategy that we are using. So we have to calculate that function, the likelihood function, a few millions times, say, for a single event. That's for one event. That's to follow up a black hole binary or a neutron star binary. Another method that we're using to do pretty much the same thing, it's called nested sampling, that was developed in the UK. Again, I won't go into details, but the main target if you're doing nested sampling is to calculate this integral, which is called the evidence. It's basically the marginalized likelihood. Doesn't really matter. The important point is that the nested sampling is a smart way of calculating this integral in a computer. And the nice thing that you can show is that as a byproduct, you have for free the posterior distribution of the parameters. So we typically, when we detect something, we run both the MCNC method, the nested sampling method, and of course we check that they agree, and they agree extremely well, as they should. But that's, it's nice. It shows us that we are doing the right thing. We did not get in any corner case of the parameter space. All right, so that's the idea. How expensive is it? So as I said, for the analysis of a signal, we need to evaluate this function here a few million times. There are a bunch of operations you are doing here. You are calculating the waveform, h. You are taking event, maybe an FFT, depending on whether the waveform is already on the frequency domain or in the time domain. And you need to do this integral, this scalar product. Now, these days, meaning the last couple of years, so for the events that we have published, detected and published, we have done this operation directly in the frequency domain, so FFT was not really, as any significant contribution in the cost of the parameter estimation. Right. So how expensive it is to do this operation, to get, a random set of parameters, putting inside this function and get a waveform? Well, it depends on the waveform model. As Alex hinted at, different waveform models contain different amount of physics. For example, some of them allow the spin to be out of, non-aligned with the angular momentum. Some of them don't. Some models have eccentricity, some don't, and so on and so forth. And that changes dramatically the amount of time that requires you to get one of these. So depending on the amount of physics you have, it can take anything from a fraction of a second, so tens of seconds or something like this, to get a single waveform, to minutes. Okay? We do have models that, take longer for them to give you a waveform than the length of the waveform. Okay, which is kind of counterintuitive. And that's for a single one, and we want millions of them. Okay? Right. So that is the difference across waveform families. Now, in the same waveform family, suppose I stick to the very fast model, which has only a line spin and no eccentricity and nothing else. Still, there is some variability that depends on the parameters themselves. And there are two main, actually, things that contribute to the cost of the waveform. One is the frequency at which you are starting your analysis. Alex mentioned that this day we start at, say, 20, 25 hertz, okay? That's because below that, and I think Andy will have something about it, we are dominated by seismic noise, so it's not worth, LIGO and Virgo are not sensitive below 20 hertz for the moment. Now, the duration of a waveform goes like f mean to the minus 1/8. So as you go to lower and lower frequency in your analysis, your waveform gets longer and longer, and hence the time to generate it also gets longer and longer. And the other main factor is the masses of the system. The duration of the waveform goes like this chirp mass to the minus 5/3. So if you are simulating very low, very light objects like neutron stars, it takes longer to generate the waveform than if you're simulating binary black holes. Okay? And also, on the top of that, the maximum frequency that you need to take care of also scale with the mass. It goes like 1 over the total mass. So heavier objects Well, you can think about it like for electromagnetic waves, right? If you have more charge, it will emit more efficiently, so it will merge quickly, right? So binary black holes end their life, say, a few hundred hertz, while binary neutron stars, they are lighter, they will go all the way to kilohertz, okay? But that is important because it changes the higher frequency you need to take care of, which affects your sampling rate. Okay, so these are all things that affect the cost of analysis, even within the same waveform family. Okay, how do I will also give number in a second, but before that, how can I make this better? So given what I told you, you can think of two possible ways in which I can reduce the runtime for the analysis of a single event. I can reduce, if I can, the number of likelihood evaluations that are needed. So if I find a better algorithm that it's more efficient and instead of 10 million evaluation only needs 1 million, I save time, of course. And we are trying this. It's part of the R&D that Alex mentioned. That's what we do in between detection. We don't only drink coffee, we drink coffee and also try to think about what happens next. The other way you can think of going is, instead of reducing the number of the likelihood evaluation, make each likelihood evaluation faster. And there are two ways that you can think of doing this. You can make the waveform evaluation faster. Remember, that's the likelihood. You need to calculate the waveform there. Or you can make this integral faster if you can, right? Is the second way. And we actually do both. They have nice names. There are ways in which you can make the waveform faster using surrogates, and Sasha will talk about it after me. These are called reduced order models, typically. And then there are smart ways in which you can make the whole integral faster, and these are called reduced order quadratures. And we are using that these days in LIGO. I will not go through the details. There is a nice paper here you can read. But the idea at the zeroth order, with many apologies for the author, for Rory, is that instead of performing the full integral, so the full sum in all the I from 0 to n, you find smart ways of only evaluating that integrand at a few subset and then interpolate in between in higher dimensionality. That's what this reduced order quadrature is. And the nice thing is that it works. In this cartoon here, in this plot, you see on the x-axis the mass of the waveform, the chirp mass of the waveform you want to simulate. And on the y-axis, you see the speed up, so that's 10 times faster, that's 100 times faster, that you get by using this arrow Q over the traditional way of doing the likelihood calculation. And you can see that depending on the mass, is in between, say a few hundreds to a factor of 10 faster. The reason why it gets better at lower masses is because lower masses waveform are longer, as I told you, so you save more, potentially. Higher mass systems are already very short, so they're already fast enough. There is not much margin to save more. Now, that's beautiful. You may tell me, okay, that our problems are solved, but in reality, there is a caveat. Not all waveform families can be used with this ROQ model. There are some caveats. Some of the waveforms we are using do not really work well with these methods. Anyhow, so times. Yeah, I'm done. Thank you, Maria. So if we use the reduced order quadrature, if we use this trick, it takes, these days, for the events that we have detected in the last few years, using a 6-course running 24/7, order of a day to estimate the parameters of a binary black hole, okay? And a few days, say to a week, to estimate the parameters of a binary neutron star. It's slower because lower mass, longer waveforms, higher sampling rate, and so on and so forth. Now, that's with this ROQ. If you need to run with a waveform family, say because you need eccentricity, that doesn't work with the ROQ, then you are worse off. And it can take weeks to months for binary neutron stars, okay, in the worst case scenario. Black holes binary are still faster because they are smaller, they are heavier. Right? So this is still an issue. There is still a lot of work going on to take care of these cases. Another important point to mention before I conclude is that these run times are for the full parameter estimation where you want information about everything, okay, from the masses to the spin to the tidal parameter. If you are after something else. If you only care about a subset of the parameters, because as Alex said before, for example, you need to send the astronomers as quick as possible the sky map. For the sky map, you don't care about the tides. You don't care about the spin either. In that case, you can try to marginalize or use smart tricks about the parameters that you do not care about, and things can get much faster. You can go down to hours or minutes. All right, and you can read these papers if you want. All right, so last slide, I promise. There are challenges ahead. First of all, as I said, none of our waveform model contains all the physics. We have a lot of models. As Alex said, they change with time, they evolve, we get more stuff. But typically we're in a situation where we have waveform model A as a spin precession but not tidal effect. Waveform B has tidal effect but not precession, and so on and so forth. And we are working toward having the Uber waveform, but the problem is that the more physics you add, the more expensive it gets. And now the other big caveat here is that LIGO and Virgo are currently only sensitive down to 20 Hertz. As they progress in the next couple of years, they will go down and get better at 10 Hertz. But as I said, the waveform cost blows up with the lower frequency. At 10 Hertz, waveforms are 6 times longer than they are now. So if now a binary neutron star is 1 minute or a few minutes, it will be 17 minutes in a few years. And there are few ideas, but we don't really know yet how to deal with this. So there is challenge going on. There is challenge to tackle for the future. And since Maria is already standing up, I will not tell you, but it's even worse for what comes after LIGO, that potentially we will have instruments in 10 or actually more 20 years that can go down to 1 Hertz. So you do the math, it's depressing. All right, so to conclude, to do parameter estimation, we use stochastic sampling, and the runtime is typically dominated by evaluating a waveform a few million times or 10 million times. And current runtimes are days to week, depending on the signal morphology and the complexity. And we can deal with this now. We can deal with this in the next science run that starts in early 2019. But as the detector gets better, we need to develop better methods and faster methods to keep up with the increasing cost of the waveform calculation. And I'll stop here. Thank you.